The shocking truth about the Manila Trench megaquake. What if I told you that beneath the pristine waters off the western coast of the Philippines lurks a geological time bomb that scientists say could unleash one of the deadliest earthquakes in modern history? The Manila Trench doesn't make headlines like the San Andreas Fault or Japan's notorious subduction zones, but this underwater canyon stretching along the western edge of the Philippines could be hiding one of the Earth's most dangerous seismic threats. This deep oceanic trench runs roughly north-south for about 1,500 kilometers, the Manila Trench, from Taiwan all the way down to Muro in the Philippines, defining the boundary where two of Earth's massive tectonic plates meet in a geological standoff. To understand why this matters, we need to explore what makes the Manila Trench particularly concerning to scientists and seismologists. Unlike typical fault lines where plates slide horizontally past each other, the Manila Trench marks a subduction zone, a place where one tectonic plate is being forced beneath another in a slow-motion collision that's been ongoing for millions of years. Specifically, the Eurasian Plate, which includes the continental shelf of Southeast Asia, is diving underneath the Philippine Sea Plate at various rates up to 100 millimeters per year in some sections. This subduction process is essentially Earth's recycling system for its crust. As one plate descends beneath another, tremendous forces build up where these plates lock against each other. When that locked boundary eventually gives way, the sudden release of energy creates an earthquake, and in subduction zones like the Manila Trench, these aren't just any earthquakes, they're potentially the largest our planet can produce. What's particularly troubling about the Manila Trench is what scientists call its seismic silence. Despite the high convergence rates between these massive plates, the historical record shows a surprising lack of major earthquakes along this structure. Since the Spanish colonization of the Philippines in the 1560s, there have been no recorded earthquakes exceeding magnitude 7.6 originating from this trench. This absence of major seismic events isn't good news, quite the opposite. It suggests what seismologists call a seismic gap, where strain energy has been accumulating without release for centuries. Think of it like stretching a rubber band. The longer you pull without letting go, the more energy gets stored, and the more violent the snap when it finally breaks. The scientific community has been conducting extensive research on this concerning phenomenon. Advanced seafloor mapping, GPS measurements, and computer modeling all suggest that the Manila Trench is accumulating what's called slip deficit, the difference between how much the plates should be moving past each other based on their known speeds, and how much they are actually moving. This deficit represents stored energy that will eventually be released. Recent studies estimate that segments of the Manila Trench could potentially generate earthquakes with magnitudes between 8.5 and potentially exceeding 9.0 on the Richter scale. For context, the devastating 2011 Tohoku earthquake that triggered the Fukushima disaster was a magnitude 9.0. The difference between each magnitude is exponential. A magnitude 9.0 earthquake releases approximately 32 times more energy than a magnitude 8.0. When we compare the Manila Trench to other subduction zones around the Pacific's Ring of Fire, the similarities become even more concerning. The geological characteristics of the Manila Trench share features with the Sumatra-Andaman subduction zone, which produced the catastrophic 2004 Indian Ocean earthquake and tsunami that killed over 230,000 people across 14 countries. Both zones have high convergent rates, extended periods of seismic quiescence, and the potential for rupturing across multiple segments simultaneously. What makes subduction zone earthquakes particularly destructive isn't just their magnitude, but their additional tsunami-generating potential. When a section of seafloor suddenly thrusts upward during a subduction earthquake, it displaces an enormous volume of water. This displacement travels as a series of waves that can cross entire ocean basins, growing taller as they approach shallower coastal waters. For the Philippines, a nation of over 7,600 islands with countless coastal communities, this dual threat of extreme ground shaking and tsunami waves represents a worst-case scenario. The science behind predicting exactly when such an earthquake might occur remains imperfect. Seismologists can identify the potential for large earthquakes based on accumulated strain, but pinpointing the timing remains impossible. This uncertainty is partly what makes the Manila Trench so concerning. We know the threat exists, but not when it will materialize. To better understand this threat, researchers are deploying increasingly sophisticated technologies. Underwater seismometers monitor the faintest movements along the trench. GPS stations throughout the Philippines track subtle shifts in the Earth's crust that might indicate changing stress patterns. Satellite observations measure the broader deformation of land masses around the subduction zone. All of these data points help scientists refine their models and improve our understanding of the potential hazard. There's also fascinating research being done on ancient tsunami deposits, layers of sand and debris carried inland by prehistoric tsunamis in coastal sediments. These geological clues help scientists reconstruct the timeline of past events and estimate recurring intervals. Some studies suggest the Manila Trench may produce major earthquakes on cycles spanning hundreds to 1,000 years, placing us well within the window for another major event. The earthquake potential of the Manila Trench doesn't exist in isolation. It's part of a complex network of fault systems throughout the Philippines, including the Philippine Fault Zone that cuts through many of the country's major islands. This creates scenarios where a major subduction zone earthquake could trigger movement along these other fault systems, potentially causing a cascade of seismic events affecting multiple regions simultaneously. In a Manila Trench rupture scenario, the immediate impact zone would experience violent ground motion lasting not seconds, but minutes. The longer an earthquake shakes, the more cumulative damage it causes. Buildings designed to withstand brief shaking begin to fatigue and ultimately fail during prolonged events. This extended duration is a hallmark of megathrust earthquakes and dramatically increases their destructive potential. The intensity of ground shaking would vary significantly across the Philippines based on distance from the rupture and local geological conditions. Western coastal regions of Luzon would likely experience the most severe effects, with modified Mercalli intensity ratings potentially reaching 9 or 10, levels at which even well-designed structures sustain heavy damage. Metro Manila, despite being farther from the trench, faces amplified risks due to portions of the city being built on soft sediments that magnify seismic waves, a phenomenon known as soil amplification. But the earthquake itself is just the beginning. Within minutes of the main shock, coastal communities would face an even more urgent threat: tsunami waves generated by the sudden displacement of the ocean floor. Computer simulations suggest that in a worst-case scenario, tsunami waves could reach western Philippine coastlines in as little as 15 to 30 minutes, giving residents precious little time to evacuate to higher ground. These tsunami waves wouldn't arrive as the dramatic walls of water often depicted in movies. Instead, they typically begin as a rapid, abnormal rise in water level, like an incredibly fast tide that keeps coming in and doesn't stop. The first wave isn't always the largest. Subsequent waves can arrive hours apart and be even more destructive. Modeling indicates that tsunami heights could range from 3 meters to potentially over 10 meters in some coastal areas of western Luzon, Palawan, and Muro, more than enough to devastate coastal communities. Metro Manila, home to over 13 million people and one of the most densely populated urban areas in the world, presents a particularly concerning vulnerability. While the capital might be somewhat protected from direct tsunami impact by its location on Manila Bay, it would face severe ground shaking complicated by its vulnerable infrastructure. Many older structures throughout the metropolis predate modern seismic building codes. Informal settlements, home to millions, are built with minimal engineering oversight and would be especially susceptible to collapse. Critical infrastructure across affected regions would face cascading failures. Power transmission systems would likely fail immediately, triggering widespread blackouts. Water systems dependent on electricity would cease functioning. Bridges and elevated roadways could collapse or become impassable, hampering evacuation and emergency response efforts. Telecommunication networks would be overwhelmed or disabled, creating an information vacuum exactly when coordination is most crucial. Have you ever considered how long your family could survive if all modern infrastructure, electricity, water, food distribution, communications, suddenly disappeared for weeks or even months? How prepared is your community for this level of disruption? Beyond the immediate impact zone, secondary hazards would multiply the disastrous effects. Landslides would be triggered throughout mountainous regions, potentially blocking evacuation routes and isolating communities. Soil liquefaction, where seemingly solid ground temporarily behaves like a liquid during intense shaking, could cause buildings to sink or tip over in areas built on reclaimed land or water-saturated soils, which include significant portions of Metro Manila's business districts. Post-earthquake fires, often caused by ruptured gas lines or electrical shorts, could spread rapidly through damaged areas where firefighting capability has been compromised.